Yeah. Hi everyone. So it's been a while. Um, so let me just like recap what we talked about last time. We introduced the notion of a Riemannian manifold. Um, and we talked about basic things such as like curvature in 2 dimensions, curvature in 3 dimensions, scalar curvature. Actually, we didn't, I don't think we talked about scalar curvature, but we talked about a lot of notions related to the idea of curvature, and all of that, depended on the fact that we had a notion of, measuring the lengths of tangent vectors. Um, so that's already really good, right? Like once we have the notion of, the length of tangent vectors, we can generalize this to the length of a curve, right, in the manifold. Um, so before I even get into like the meat and potatoes of what I wanted to talk about today, let's, just take a second and um let's look at let's look at like R2, right? Let's look at R2, and let's say we wanted to find the distance between 2 points in R2 um that is joined by like a smooth curve, right? Let's restrict ourselves to smooth curves because that's what we've been dealing with. So let's look at that, and if you recall, we talked about what the distance should be, right? So if you remember, the length of a curve connecting 2 points is simply the integral from the initial time to the final time, uh, ti to tf, and it's the square root of, in this case, I'll write it like this: x dot squared y dot squared dt. Right? We talked about this like way back when we started talking about, integrals um, in like multiple dimensions. Um, but okay, and this is wonderful, right? Like this is great. But one thing to note is that I want to write this in terms of not I don't want to write this in terms of X and Y, but rather I want to write it in terms of my Riemannian metric, right? Because R2 comes equipped with the standard Riemannian metric. So I want to rewrite this a little bit. Um, and if we look at it hard enough, we can note the following, right? If we have some curve, right? Let's say this is our manifold. G, it has some Riemannian metric. Say these two are points, and this is like some curve phi that connects them. Now, what is x dot, right? Like what exactly is x dot? It's basically like if I take the velocity vector phi dot, I look at its x component, that's what x dot is, right? But I know exactly what the length of phi dot should be. So in coordinates, I know that the length of phi dot is, well, the inner product of phi dot at the point P with itself, right? I mean, this doesn't depend on any coordinates, but if I wanted to write this in terms of coordinates, this would be Gij phi dot I phi dot j, all at the point P, but I'll suppress that notation, right? And now if we look back at what this thing is, this is simply, I mean, in terms of this thing, um, sorry, if we come back to this, the infinitesimal, this is like the distance squared, right? This is like distance squared. And now the length of my curve is simply the integral of the dis like this of the it's just the integral or like over time of the speed of my curve, right? But my speed is given by the square root of this, right? Um Gij phi dot I phi dot j, which then tells me that the length of my curve phi, which I'll just write like this, should be defined as the integral from the initial time to the final time of the square root um, of this. Are there any questions on the definition of the length of a curve in a Riemannian manifold? and why it should be defined this way. Okay. With this out of the way, I mean, we can rewrite this in like a nicer way, I guess. It would just be like this. Okay. But okay, that's not too important. What's really important is we want to like figure out, given any 2 points, is there a curve that has the minimum distance, right? Has the minimum distance between the 2 points. How do we find that out, right? How do we like find a curve that minimizes the distance between 2 points? So we know that in the standard, in like R2 or even in Rn, it's intuitively clear to us that with from all smooth curves, the curve that minimizes the distance is simply the straight line, right? That's pretty, I think it's pretty easy to see that that's the case. Well, at least intuitively, but we haven't proven it, but intuitively that should be the case. Um, but now my question is like, does such a minimum always exist to begin with? Like before we even tackle the question of can we find such a minimum, we must answer the question, does such a minimum always exist? And the answer is no, right? The answer is clearly no. Um, for one, if my manifold is, disconnected like this, there's no continuous curve that goes from this point to this point, right? So the answer is so let me just write this down. Okay, but now you might tell me, okay, Chris, this is like not a very fun example because there's no path between them to begin with. So how can we even talk about a minimizing path? Um, but fret not, we can construct an even better example, right? Let's look at R2, but now let's remove the origin. Okay, let's look at R2 and remove the origin. And now let's look at this point and this point. There's no straight line that goes from point A to point B, right? So intuitively, there's no minimum path, right? There's just no minimum path. There's a minimum distance between them, right? Because we know that the distance between A and B in this case should be 4. So there's a path that gets as close to 4 in length as we want, right? But never actually gets to 4. But okay, now you might tell me, okay, this is not simply connected. Is there a simply connected example where, you still don't minimize distances? And the answer is yes. Just look at R3, right? Just take R3 to move a point, no longer simply, I mean, it is simply connected now. Um, but the same issue happens. You can get a path that is as close to the true distance as you want, but you can never actually minimize the distance. Okay. So now this might feel like, not the best start. Um, but let's sweep these issues under the rug for now. Um, because as it turns out, given any path, given any 2 points, right, there is a curve that locally minimizes the distance. So if I take like a point and then I look in like a neighborhood, like a small enough neighborhood, I can find paths um, to these points um, that have like, the distance, that minimize the distance. And these curves are called geodesics. Okay. So in our case, geodesics are curves that attain minimum distance. Oh, sorry, minimum length. Length. Okay. So if I connect any 2 points, and again, when I say curves, I mean, rectifiable, um, smooth. So we don't want any like infinite, we don't want infinities floating around, basically. Okay. with this, now let's come back to the length function, right? Because now our goal is to minimize sort of this length function. And let's sort of look at what the general what the general structure of this length function is, right? Firstly, we note that it's a linear functional. Um, it's a linear functional in is it a linear functional? It's not quite a linear functional, but I mean it's a function on curves, right? So let's look at what the length function is. So the length function takes curves, takes smooth curves, um, to a real number. Okay. And now our goal is to like minimize this number and like find a curve that minimizes the curve, like minimizes this. But as we've seen, such a curve may not exist. So we do the next best thing, which is like local existence of such curves. And as we'll see today, hopefully, you are guaranteed local existence of geodesics, right? You might not be able to patch all of them up together to get a geodesic, but locally you can find geodesics. Okay. So I'm gonna, write this in a little more physics sort of notation. Um, and I'm gonna write it like this, and it's just gonna be the integral from some initial time to some final time of some function L that will depend on phi, will depend on phi dot. Okay. For now, we won't allow it to depend on the time parameter, and we won't allow it to depend on higher order derivatives because as we've seen, for example, the length function already, I mean, it only uses the velocities. So for us, this is good enough for now. Um, okay. And now the idea is that we want to sort of find extrema of this function, right? And we're going to take ideas from like calculus, and we're going to say, okay, if I vary this function a little bit, if I add a small um, parameter, like if I vary the phi function around a little bit by adding some variation to it, I want that at an extremum, I want this variation to be zero, right? Up to first order. Like I want like the first order approximation to be zero, right? So the way we write this is okay, we're gonna take phi and we're gonna map it to like phi plus delta phi. And now what we're going to do is we're going to take S applied to phi plus delta phi and S at phi, and we're going to subtract them, and up to first order, we want them to equal zero. So that's precisely what we're going to do. I mean, it's hopefully this is clear to see just by linearity of everything. Um, okay. Then what we're going to note is that S at phi plus delta phi minus S at phi is equal to. But now the idea is that we want this variation term to go to zero, right? And one way to like in such a limit, right? In such a limit, this term just looks like we're taking the derivative of L, right? In such a limit. It looks like we're taking the derivative of L. And that's exactly what it is, right? So for now, I'm gonna write this like approximation because it whenever I write this approximation, I mean we're taking like a limit. Um, and now all this is, and then we use chain rule to get that this is partial L partial phi with a variation in phi. Actually, we can write this a little better. So if I just look at this L term a little better, right? Let's come to the side a little bit and let's look at this L term a little better. Now I can find its first order Taylor approximation, right? And it's going to be L at phi dot plus the derivative of L, in the sense of the like Frechet or Gato derivative, whichever one. It turns out in this case we only really care about the the Frechet derivative, which is technically stronger than the Gato derivative, but that's fine. Um, and then it's going to be at the variation, so it's going to be delta phi dot plus like high order terms. So what this is saying is that L at phi plus delta phi dot plus delta phi dot minus L at phi dot is simply approximately equal to partial L partial phi delta phi plus partial L, actually it's equal to exactly delta phi dot plus other, right? But in the limit, these other terms will not matter, at least in the first order approximation. So we're just going to ignore them. So what this says now is that we get this dt. But the way the variation was defined is, it tells you clearly that the variation of phi dot is the same thing as the derivative of the variation of phi, right? This is built into the definition of the variation of phi dot. So what this is saying is that we have something like this. Okay. Now, in this case, it would be very convenient if we had this phi dot, you know, in such a way that we can factor out the phi dot, right, and get a term, because then we can use a theorem from real analysis to then conclude that something must be zero in order for this to be an extremum. So the way we're going to do this is we're going to realize that this is something times the derivative with respect to t, and we're taking the integral, so we can use integration by parts. Okay. So let's make use of integration by parts. Let's write this term out. And now by integration by parts, we're going to get a partial L partial phi dot, and then the variation in phi evaluated between Ti and Tf. Okay, minus the integral from Ti to Tf of partial L partial phi dot, sorry, d by dt, partial L partial phi dot delta phi dt, which now tells me, partial L partial phi minus d by dt, partial L partial phi dot delta phi dt, plus some boundary terms. Okay. And all of this, by the way, we want equal to 0. So something, I mean, like up to first order, right? So something very interesting has happened. We somehow took, something in terms of an integral of some function, and to minimize this, we took derivatives. And it almost sort of looks like um, it almost sort of looks like we've reduced an integral minimization problem into a differential equation, right? I mean, that's practically what we've done. We've taken a question about, I want to minimize this curve. Like I want to minimize the length of this curve. And all that's done now is it's, reduced the problem down to like these formal variables. Because again, remember, phi and phi dot, in some sense, live in some function space. So all these derivatives we're doing are like they're Frechet derivatives, right? This is why we needed to introduce like the heavy machinery that we did when we started talking about differential calculus. It's because it's no longer the case that the regular old derivative, suffices because now in this case, this function depends on other functions, as in it is a function of functions, right? Not in the chain rule sort of sense, but it is like actually on a function space. Um, so okay. Now, in the case of minimizing distances between two fixed points, right? This boundary term is not very interesting. And the reason for this is like at the endpoints, the variation must vanish. And since the variation vanishes, all we get is that this integral is zero. Okay? So in the case that the endpoints stay fixed, we get that the variation at the initial time and the final time is equal to zero, right? Which means that we have no boundary terms, hence no boundary terms. But okay, that's fine and dandy, right? Um, but is there any interesting physics that happens with the boundary terms, right? So, like, is there anything interesting that happens if I allow boundary terms, for example? Um, and the answer is definitely yes. So when in a couple of moments, when we talk about the principle of minimum act or the extremized action or the principle of least action, we'll see that in the usual formalism, we don't allow for such boundary terms. However, when we start talking about things like string theory, these boundary terms actually play a huge role in, defining the evolution equations for both open and closed strings. Okay, and then these give you very interesting dynamics. Um, and because of that, I will leave as an exercise, to think about like in the problem sheet, I will put a couple of like minimization questions or like extremization questions, where I want you to, do a similar procedure and then arrive at a system of ODEs if to arrive at a system of ODEs with certain boundary conditions, solve those ODEs and stuff like that. So for now, I'll just take fixed boundary points, but do remember that, allowing the boundary points to like not stay fixed is also very interesting in its own right. And it does lead to very interesting physics. But for now, we will take that the boundary terms are fixed. Are there any questions on this so far? Okay. So there are no boundary terms, hence the integral of partial L partial phi minus d by dt partial L partial phi dot dt equals zero for all variations keeping endpoints fixed. Okay, that is very important. That the variation does not change like the boundary terms is actually very important because if you allow for variations to change boundary terms, you actually get this extra term as we talked about. Okay, this question also now doesn't really look much easier, right? Like how do we even recover like phi from this, right? Like that makes no sense for now. But it is not a hard exercise to show that if, phi is compactly supported and smooth, um, and the integral of phi times f equals zero for all such phi, then f must be zero. Okay, this is an exercise. So exercise, show that if phi is C infinity compactly supported in TITF and F is integrable and the integral ti to tf of f phi equals 0 for all such phi, then f equals 0. I mean, f equals 0 up to measure 0 again, but for all intents and purposes, since we're choosing the smooth function, it should be 0. Because if you had a smooth function that only differed at, points of measure 0, it's no longer the same function because of like smoothness. Okay, so what this actually tells you now is to solve for such phi, we must solve um, the differential equation, you know, this with phi of ti equal to a and phi of tf equal to b. Okay, so we have this second order. Oh, sorry, this should be phi dot. So we have this like sort of second order differential equation looking thing with two initial conditions, which means that we have enough information to solve solve the ODE locally, right? So this sort of tells us that you have an extremized thing locally that like solves this ODE. This ODE is called the Euler-Lagrange equations. So this is called the Euler-Lagrange equation. Okay. And this is like one of the most important differential equations in physics. Because a lot of physics is you can now like talk about the dynamics of a lot of things using this simple looking equation, right? But to talk about physics, we need a like useful sense of what this L function should be, right? Like not every like say I have some physical system. I firstly, how do I even think about what L should be, right? That like how can a like what type of function should I have that um describes the motion of particles in this system, right? That's a central question. Another central question is like I already have uh, I already have a like way of solving for dynamics of particles, which is Newton's equations. So is how do I make it so that this function not only gives me the like describes the system but also agrees with Newton, right? Um, well, again, agrees with Newton in a classical limit. For this, I would highly recommend reading page. Let me just check my notes actually. Page 6 and 7 of Landau Lifshitz, volume 1. Um, they talk about, what a good choice of this L function should be in a classical limit. Um, and as we'll see in physics, the this L function in the classical limit should be a difference between the kinetic energy and the potential energy. And they also explain why the kinetic energy is 1/2 mv squared. Well, for our cases, it makes sense that the kinetic energy is 1/2 mv squared because if we look back at what our motivating example was, we looked at like things that minimize the distance and v like minimizing v squared, as it turns out, is equivalent to minimizing this like the square root of v squared or like the speed. Okay, so are there any questions so far? Okay, with all of this out of the way, let's actually go back to the question at hand and let's, try to find what this L function is to begin with. And not only find the L function, let's also, find the Euler-Lagrange equations for this L function. Um, and let's see. Okay, so going back to the distance function. Note in this case that L is actually a function of four variables, you could think, x, y, x dot, y dot. And all it was is it gave you the square root of x dot squared plus y dot squared. Okay. One thing to note is that L doesn't actually depend on the position, like the place you are, right? Um, I, it turns out that this is actually a very important observation, that this doesn't immediately depend on these variables. In physics, if you have this L function, which from now on I'll call the Lagrangian, if you ever have that the Lagrangian doesn't depend on the position, quote unquote, variables, we call that a cyclic coordinate. Okay. So I'll describe it more formally in a little bit. But for now, we have this. And now you might tell me, okay, L had to be a function of, a curve and its derivative. But that's exactly what this is, right? Like x, y, x dot, y dot are curves, technically, that are parameterized by this variable t that we don't really make an explicit mention of. Okay. So let's now find the Euler-Lagrange equations. One thing to note is that, you get an Euler-Lagrange equation for each position coordinate. Um, and the proof is exactly the same as above. You can check that you'll get exactly that. So let's just find the Euler-Lagrange equations really quickly. So first we have to compute partial L partial x, but that's zero. Partial L partial y is also zero. Partial L partial x dot is, what is it? It's x dot times x dot squared plus y dot squared to the negative 1/2. And partial L partial y dot is equal to y dot times y dot squared plus y dot, oh sorry, y dot times y x dot squared plus y dot squared to the negative 1. What this now tells us is that d by dt of partial L partial x dot equals partial L partial x, um, which means that x double dot, okay, I'm just not gonna say it again and again, but it's just this. Um, and similarly for the y coordinate. Okay. Okay, now this looks absolutely painful to solve. Um, but again, we know that, you know, we're hoping that straight lines are solutions, right? And now we're going to use a very nice theorem from ODEs to be like, okay, we're going to use Picard-Lindelof, basically. Um, and with that, we're just going to guess a solution and then hope that that solution, I mean, Picard-Lindelof will guarantee that this will have, um, I mean, okay, you have to be slightly careful because 1 over the square root of x is not really Lifshitz, or is it? I don't know. Mm. Mm. It's only non-Lifshitz, I think, around. Let me actually check. Okay, it is Lifshitz as long as you don't include zero. Um, they're locally Lifshitz, so that's all you really care about for Picard-Lindelof. Um, so Picard-Lindelof will apply here. Um, Again, I mean, as long as you don't go to zero, stuff like that. So with that in mind, we're gonna guess solutions x of t equals t x1 plus 1 minus t x2 and y of t equal t y1 plus 1 minus t y2. If you can draw this out, and this will just be a straight line, which then tells me that x dot is simply equal to x1 minus x2, and y dot is simply y1 minus y2. So as we can see, the only trouble point is if x1 and x2 are the same and y1 and y2 are the same, right? So in that case, the minimum, excuse me, the minimizing curve is just don't move. Right? So we don't really have to worry about that too much. So now we can assume at least one of them is not the same. And since that's the case, we can then get that, it's Lipschitz in that domain, which then tells me that x double dot is equal to 0 and y double dot is equal to 0. Moreover, um, the squares of x dot and y dot are constant. Hence their sum is constant. Hence their square root is constant, which means that this term is also just 0. So this, tells this satisfies the Euler-Lagrange equations. This satisfies the Euler-Lagrange equation. Okay. Now I will leave this as an exercise, how to show that this is actually a minimum. Because the Euler-Lagrange equations actually just guarantee that it extremizes the action. So for all we know, we could have actually maximized the action. We could have maximized this like length function, right? Instead of minimizing it. So how do we actually check that it's a minimum? I will outline a proof in the next problem sheet. Um, but okay, are there any questions for now?
To check that it can't be a maximum, can't we just take, so like if the length function maximized the action, then couldn't we just find an even bigger length function so it can't actually maximize it?
Um, well, kind of. I mean, the idea is that like since we're using methods from calculus, the method we've used is, set the derivative of the function equal to 0 and then solve. But that, if you recall, doesn't actually give you that it's a global maximum or a global minimum, or it doesn't even tell you if it's a maximum or a minimum, right? All it tells you is that you're at some like critical point. This critical point may be a global maximum, maybe a global minimum, maybe neither. Um, and if it is a maximum or a minimum, it might not be a global maximum or a global minimum, right? It could be like a local maximum or local minimum. So just finding a function that, gives you something bigger or gives you something smaller doesn't necessarily mean you're not a minimum, if that sort of makes sense.
Sure.
You seem unsure with my answer. Okay. So I'm guessing I'm hoping at least that you sort of see that we need to be slightly careful when we're talking about these things because um like I just said, just because you satisfy the Euler-Lagrange equations, you don't actually get for free that it's maximized or minimized or extremized. As you get that it's extremized um, locally. Okay. With this out of the way, like we've now talked about one of the most important, um, well, I want to say discoveries, but it's not really a discovery, of physics, which is that instead of solving Newton's equations, we can sort of solve this new type of equation, like this system of second order equations, and we get the same sort of result. Again, please read Landau Lifshitz to see, the build up to this, because I'm avoiding that. But from a mathematical setting, we basically have that we have a function that takes in um so if we look at what L actually is, right? It takes in a set of it takes in a position and it takes in velocities. But what sort of object gives you positions and velocities in one? It's nothing but the tangent bundle, right? So from a mathematical standpoint, the Lagrangian is just like it's just so. Then let me just from a mathematical standpoint, L goes from the tangent bundle into R. It doesn't have to be, um, it doesn't have to be linear on each fiber. Um, it doesn't have to do like satisfy any properties. All it has to be is a smooth, right? We will call M the configuration space. I'll call L the configuration space and L the Lagrangian. I mean, this function could be any smooth function. So for now, it doesn't really matter if it's describing something physical or not. It's just called a Lagrangian regardless. So given the exposition and Landau-Lifshitz, um, we will mainly look at Lagrangians that are a kinetic energy term minus a potential energy term for now. Okay. Um, so in classical physics, um, we usually take L to be kinetic energy minus potential energy. And from the exposition and Landau-Lifshitz, which in standard Rn is so the kinetic energy is equal to 1/2 mv squared, and the potential energy could be a function of whatever. Like the potential energy is also just a function on its own, and potential energy is also just a function on the tangent bundle, right? It could be anything. Um, Usually, though, like in classical physics, we see that the potential energy only depends on the position rather than the velocities. Um, but even in classical physics, that sort of like falls short. Because, for example, if you have like electromagnetism, right, the magnetic field induces a force that depends, like the potential energy depends on the velocities of your particle. So for now, we will like look at when the potential energy is, a function of both the positions and the velocities. We will not really discriminate. But now, what is 1/2 mv squared really mean in um like on a manifold, right? So now there's actually a couple fun ways to think about what mass means mathematically. So in one end, like you could have mass just be, it's a thing on its own, but you could also have mass be, embedded into like the geometry of M itself. Okay. Um, so if we look back at the length of something, it had G, Gij, phi dot I, phi dot J. So that means that, if you had a particle of mass M in Rn, its Riemannian metric, or the Riemannian metric of its configuration space, would just be M. So if we had a particle of mass M, its kinetic energy, say its configuration space, I mean M is like it has to come equipped, like in the situations we'll be dealing with, M will come equipped with a Riemannian metric that'll tell us information about the mass, the curvature of the path it'll take, etc. So if we had a particle of mass M, its configuration space, let's talk about Rn for now, because let's if we had a particle of mass m in free space, um, then its configuration space is um Rn with a Riemannian metric um Gij equal m times delta ij. And why do we decide to do this? Because if we now look at 1/2 m, so if we look at 1/2 v squared, this is just equal to 1/2 Gij vi vj, which is just 1/2 m v squared. Okay. Does this make sense? So in some sense, actually, do I have this written correctly? Hmm. Yeah. This will technically be mv squared like this. So it now, okay. Now its kinetic energy will then be 1/2 Gij vi vj. Okay, and then you can check that this is the same thing as saying that its kinetic energy is 1/2 mv squared. But okay, with this, let's now, define some Lagrangians and let's see if, things actually make sense. So if I have a free particle, right, it so if we have a free particle, um, then its Lagrangian is just its kinetic energy, which is 1/2 Gij vi vj, or written more explicitly, it's 1/2 Gij x dot I x dot j. So now let's find the Euler-Lagrange equations, right? Because we're sort of saying that this Lagrangian, it's the action that it has, its extremal curves give us dynamics of particles. So let's, actually make sure that makes sense to us. Um, so if we look at partial L, partial x, this is nothing but 0, right? Because in this case, remember, this is 1/2 m delta ij x dot I x dot j. Um, and if we look at partial L partial x dot k, this is equal to 1/2 m delta ij um, partial x dot k x dot I x dot k x dot j. And now using the product rule, this simplifies down to 2 delta ik x dot j, which is the same thing as m delta kj x dot j. Okay. Hence, we get d by dt. And now if I take d by dt of this thing, I just get m delta kj x double dot j equals 0. Right? Which tells me that x double dot k equals 0, right? Which means that hence the particle moves at constant velocity. not only does the particle move at constant velocity, we get that m x dot k is conserved along the motion. Right? We get that directly from the Euler-Lagrange equations because we get d by dt of this object is equal to 0. And now setting j equals k, we get precisely this equation, right? And we remember we know what this is, right? This is linear momentum, and like from what we've seen in like physics. This is linear momentum. So not only did we get an equation of motion, we also got a conserved quantity for free. Now, this is a very, very deep theorem by Emmy Noether that I will outline as a proof in the next problem sheet, um, as an exercise, sorry, in the next problem sheet, which says that if I have some transformation of the coordinates um, that leaves the Lagrangian invariant, then there must be some conserved quantity associated to that transformation. And not only this, it also works the other way around. If there were such a conservation law, we must have like change of coordinates or a coordinate transformation that keeps the Lagrangian invariant. This is an extremely profound theorem in physics. I feel like not enough people talk about it. Um, it is, I mean, it like changes, it basically trivializes a lot of very, very hard problems because you can find conserved quantities, which then leads you to be able to actually solve the system of equations in any meaningful way. Um, enough about that, I think. Also, one like one very important consequence of this actually is that so when Einstein wrote down his field equations, he was a bit worried because it didn't look like things were conserved in the galaxy, in the universe, right? Um, it turned out that certain things that should be conserved were no longer conserved if you look at them in the normal sense. It took this brilliant insight by Emmy Noether to actually come up with the fact that things are conserved, but not in the usual sense, but they're conserved covariantly, which we will describe like in the next meeting. So Emmy Noether is amazing. A lot of the things she worked on are just amazing, and again, I don't think enough people talk about this. But okay, enough about that. Let's move on. So, okay, you can check that, okay, this works in a free particle. You can also now check, so exercise actually, exercise. Um, let m equal s1 and g equal delta uh, d theta squared. Um, what is the kinetic energy? Kinetic energy. Actually, what does the coordinate mean? What does theta dot mean? What is the kinetic energy? What does it mean, etc. Um, and yeah, find the equations of motion. Let's actually do S1. r and then r squared d theta. You can get this from a change of coordinates. So hint x equals r cosine theta, y equals r sine theta, and then you can do things with it. Okay. With this out of the way, there's just two more things I want to talk about today. And one of them is, as we talked about last time, on each tangent space, um, sorry, one second. Okay. So now, given that, on a general Riemannian manifold, so on a general Riemannian manifold, we have a very nice Lagrangian, right? We have L of we have a nice Lagrangian. Oh, Lagrange, Lagrangian, Lagrangian. Why am I struggling? Lagrangian. Oh my God. Sorry about that. We have a nice Lagrangian in which in local coordinates is given by um, 1/2 Gij Vi Vj. Okay, but I like the coordinates x dot I x dot j more, so I'm gonna write it like this. Now we need to, talk a little bit more about this. So we have so on each tangent space, G at P, takes in two things and gives you a number, is um is non-degenerate, right? Since it's non-degenerate, this means the induced induced map GP hat from TP into TP star is an isomorphism. It also turns out that this is actually the Ries isomorphism, which is, even better. Um, but okay, it's an isomorphism. Recall that this is a tensor, right? It's a tensor, which means that you can actually look at it as the tensor product of two things. And so if you just include into the first variable, you're left with the second thing, but that second thing is a tensor. So make sure that this actually makes sense to you. Um, so in local coordinates, right? What is this isomorphism actually doing? So it's not even in local coordinates. So it takes in a point V, right? And all it does is it puts V into the first slot and gives you that linear functional. Um, I like to write this as the interior product of G of V with G. But now let's say you had some basis and then you like, I mean, let's say you had like the standard basis or whatever, it doesn't actually matter too much. In which case, G equals Gij dxi um tensor dxj. Um, right. This means that hence G hat, right? What G hat would look like in these coordinates is so it takes in Let's actually write this out. So hence if V equals VI partial I, actually let's do VK partial K, then G hat of V with nothing would just be Gij um VK sorry, dx I VK partial K dx dxj, which simplifies down to ij v I dxj. Okay. Um, does this computation make sense? Okay. Um, so basically we get um so in local coordinates, so hence in local coordinates, um this sort of looks like actually I mean this is already what it looks like. It looks like this linear function. I'm not sure what else I'm trying to say. Okay. Um, but now we actually get an inverse of this map, right? We get an inverse. G hat inverse at P, which takes TP star M into TPM. Um, right? Such that like in local coordinates, you have G hat inverse P is equal to Gij partial xi tensor partial xj. Um, and Gij satisfies delta ik. I mean, that's just what it means to be inverses of each other. And now we can actually use this to raise and lower indices. Because look at this, right? If you contract I and j, you get vi. So you get vj, right? Which now has a lower index. Similarly, you can use this index to raise indices. So if you have covectors, you can make them vectors by raising their index. If you have a vector, you can make it a covector by lowering its index. If you have, multi-vectors, you can do so on and so forth. Okay. And now we will now use this fact. Okay. So let's now look at the Lagrangian, which was just 1/2 Gij x dot I x dot j. And now let's find its Euler-Lagrange equations. I'll just call them EL equations. Okay, very simple. Let's just start with this. And now note that in this case, the GIJs, like they do depend on the coordinates, right? They a priori might depend on the coordinates. So we have to take that into account. Um, but they don't actually depend on the tangent vectors themselves. Okay, so remember on each on each fiber, um, it's it's like a constant functional, basically. So this just gives you 1/2 partial k gij. And now, I mean, the velocity, like the basically how you want to think about partial k is it's a vector field that points orthogonally to like each fiber because it moves you along the manifold and not along the fiber. So if I take the partial along the fiber, the fiber component of this, so if my fiber is like this looks like it's an orthogonal component. So its fiber component is 0, so it's actually independent, because they're independent coordinates. Right? Um, I'm not sure I had to explain it in that much detail, but I hope that makes sense. So, uh, after like, I don't have to do any product rule. It's basically what I get out of this. Um, and if I take it with respect to this, I get 1/2 Gij partial k x dot I x dot j, which if you recall just gives you 1/2. Gij delta ik. And now the indices, like if they're up or down, actually matter. So let's be careful with that. And then, just doing some index manipulation, you get that this is GKJ. If I wanted to, I might also write it as lower indices. Okay. And now let's take d by dt of this. And I'll actually make use of this. Making use of that, we get that this is partial double dot j gkj plus x dot j partial I gkj x dot I. And this comes from chain rule. Um, sorry. Oh, okay, I just wrote it weirdly in my notes. Okay, so hence, what do we get? We get, um, let me just write this out. We get this 1/2 partial k gij x dot I x dot j. Okay, now what I'm gonna do, right, is I'm gonna realize that in this setting, it doesn't matter if I wrote ij or ji. So I can like swap indices. Doing so, I get the exact same thing as this. So if I add that, I actually have to divide by 2. Okay. So this leads me to the following. So I get partial I j k. Well, let me actually write this a little nicer. So 1/2 partial I j k j plus partial j g k I minus this term partial k g I k g I j partial sorry x dot I x dot j equals 0. And now what I'm gonna do is I'm gonna like raise the indices to get g k alpha x double dot j g k j plus 1/2 g k alpha, all this other stuff. Okay. And what do we get here? From here we get a delta alpha j x double dot j plus 1/2. Sorry, I'm not call this 1/2. I'll call this thing over here. I'll give it a special name. I'll call it gamma. Um, I'll call it gamma alpha. So I'll call it gamma kij, which gets me gamma kij x dot I x dot j. I'm not sure why I removed that. Equals 0. It looks like I've made a index mistake, which is sad. How I made an index error? Hmm. So if I oh god. Okay. Oh. Okay. So if I call this x double dot k, that makes it that. Oh, there should be alpha here. Okay. Sorry about that. There should be alpha over here. And what that ends me off with is x double dot alpha plus gamma alpha ij x dot I x dot j equals 0. Okay. These are now, lo in local coordinates, locally, the geodesic equations, right? These give you the equations that describe a geodesic. And moreover, we get these n cubed functions. So the n cubed functions, alpha ij, are called the Christoffel symbols, right? We'll see later on that Christoffel symbols don't actually depend on the metric. However, if we want certain nice properties regarding, these objects called connections, these Christoffel symbols are, the best choice. And we'll actually see that given those unique properties, this is actually the unique collection of n cubed Christoffel symbols that give us um, those nice properties on the connection, whatever that is. We'll talk about the connection next time. But okay, if so, are there any questions? Okay, if there are not any questions, I will call it a day. And then I will see you guys on Tuesday. Okay, bye-bye.